problem 7 from chapter 7 of Introduction to Statistical Mechanics by Roger Bowler. This chapter is related to Maxwell distribution of molecular speeds, and the problem is related to density of states. Alright, before that video we have already uploaded some of the problems related to this chapter, and these problems include 7.1, 7.3, 7.15, 7.17, which means 15, 17, 6, 3 and 1. All these problems are already been uploaded, and all of these were related to density of states topic. That is why I uploaded them or next to each other. All other problems in between are related to mean square speeds and Maxwell distribution of molecular speeds in particular. So I will upload them one by one and next to each other so that it makes sense, because all of them are closely related. In this video we are going to solve the problem 7. Let's see the problem statement, and we have this problem statement here. Okay, as you can see right here, this is the problem 7. Calculate the partition function for a relativistic particle whose p is very greater than mc in one dimension. So taking a one-dimensional case, we need to calculate the partition function for a relativistic particle. Before that, in problem 6 we saw a 3D system in which we calculated the density of states in energy for that relativistic particle, and we calculated the partition function for an relativistic ideal gas. So yeah, now let's see how we can solve that problem. We need to calculate the partition function. So we know that the partition function in terms of density of states is given by partition function is given by, this formula remains same whether it is a 1D case, 2D case or a 3D case. The only difference comes in when we put the values here. Okay, these values are maybe different for different dimensions. Okay, but the basic or general formula remains the same for partition function. If it is a 3D case, you will use the same basic formula. If it is a 2D case, similar formula will work, and if it is a 1D case, the same formula will work, as we will see in later videos for different problems from the chapter. And okay, and d of k, this is density of states. I was thinking something else and I just wrote the same formula again. Let us call this equation as equation number 1. You have to write it once. I just wrote it mistakenly because I was thinking something else. And yeah, we need to calculate the partition function in one dimension. So we know that the density of states in 1D is given by, you'll write that here. Okay, density of states in 1D is given by this formula, this simple formula. Okay, and for a relativistic particle, what else needs to be inserted into this expression is besides d of k, as we know d of k is L by pi, we should know the energy expression as well, which is E of k. And we know that for a relativistic particle whose p is very much greater than mc, okay, rest mass whose kinetic energy or something like that is very greater than its rest mass, then its energy is approximately equals to pc. Okay, and p is since equals to h cut k, so instead of p we'll write h cut k in c as it is. So E h cut kc is the energy expression that will insert into this expression number 1. So let's insert all both of these expressions 2 and 3 into 1, and we got this is integral from 0 to infinity. D of k is L by pi, dk remains the same because it's a part of integral, and e to the power minus, instead of e you'll write h cut kc. Okay, divided by kbt. Be mindful of this k and this kb. This is Boltzmann constant and this is wave vector. Remember to put b in subscript of that Boltzmann constant to make a difference, because I normally confuse them because I just usually forgot to put b in the subscript. So it's L by pi dk. Let me separate the constants and variable. Variable here is k because the integral is on k variable. You can see the differential here. So h cut c by kbt, these are constants here, and k is the variable. Now we'll take L by pi outside of this integral because L and pi are constants and they doesn't contain k in it, so they are constants, and we are left with this expression. This is a very easy integral now, and its integration is simply this exponential function as it is divided by the derivative of its power. It's only true if we have k to the power 1 here. If it would have been k square or k cube, we couldn't use this formula. Okay, then we have to use some other method to solve it. It's only true if it's k to the power 1 here. Okay, e to the power k and some constant being multiplied. If it would have been e to the power some constant multiplied k square, k cube, k4 or something like that, then we couldn't use that formula. We should know the limitations of our formula. We need to take the derivative of power. Power is minus h cut c by kbt into k also. L by and limit of integration, don't forget that, and yeah, minus h cut c by kbt into k. We'll put the limit of integration after we simplify the denominator. We know that minus h cut c by kbt is constant, so they will come out of the differentiation. D by dk will be applied on k, and we don't know that the derivative of k is 1, so it's 1 here. We'll take this thing outside of the integral. This kbt in denominator of a denominator will come above here. L kbt divided by pi h cut c, negative sign here. Okay, minus h cut c by kbt k, and limit of integration. Now let's apply the limit of integration here. Minus the L kbt pi h cut c, upper limit minus lower limit, so minus h cut c by kb, oh it's t here, t. Upper limit here is infinity. We'll put it in place of k because we know the variable was k, so it's infinity here, minus e to the power 0, simply because we'll put 0 in place of k, and k 0 multiplies with the whole power to make it 0 as a whole. That is why I just wrote 0 alone here, because we know that it multiplies. Infinity multiplies with that constant to give infinity again, but negative infinity. Be mindful of the sign. E to the power 0 is 1. Okay, e to the power minus infinity, e to the power minus infinity, we can write it as e to the power 1 over e to the power infinity with positive power. Now if infinity is in power of a positive number or something like that, or negative number or whatever it is, the result is again infinity. Okay, and 1 over infinity we all know is equals to 0, so the result here is 0 minus 1. So we are left with 0 minus 1 is minus 1. This minus and minus cancels out, and we are left with L kbt by pi h cut c, and this is the partition function for a relativistic particle in one dimension. Okay, this is the final answer, and I hope you understood it. It's very easy. Okay, you just need to remember the formulas, and you just should know the density of states, you know, um formulas as well. Okay, and you just need to put them here. In 2D, 3D and 1D, density of states had different formula. In 2D we have ak by 2 pi, in 1D we have l by pi, in 3D we have vk square by 2 pi square. If you have to put in k space, okay, but if you need to put in e space, then you first have to find out the density of state in e space. Sometimes it's given and sometimes it's not. So this is the way how you convert from k space to e space using this formula, and you can simply then use this formula as well in completely in completely e space. Okay, it's dependent upon what's given to you. Okay, so it's optional. I prefer in k space, but sometimes it's specially mentioned that you have to do the calculation in e space. Totally up to you. And yeah, I just needed to mention that you can do it this way also, but in k space is way easier. And yes, we'll meet you in next problem. Good luck.